Hello friends. So today we are going to discuss the questions from the year 2023, and there are total number of 21 questions, and a combination of both mains as well as advanced. First question, and it states that a monochromatic light wave with a wavelength lambda 1 and frequency nu 1 in air enters another medium if the angle of incidence and the angle of refraction of the at the interface are 45 and 30 degree respectively, then the wavelength lambda 2 and the frequency nu 2 of the refracted wave is. So here we are going to find out the wavelength and frequency in the, you can say, the refracted wave, after refraction. So here we are given two things. We are given the incident wavelength, that is lambda 1, we have incident wavelength lambda 1, then we have incident angle let us call that as I, which is given as 45 degree, and then we have refracted wavelength, incident wavelength, and also we are given incident frequency. That is called as a nu 1. Then we are given a refracted wavelength, lambda 2, a refracted angle, let us call that R, and which is given as 30 degree, and we are also given a refracted frequency. And that is given as nu 2. So first of all, we are going to find out our, you can say, the refractive index of the medium, because it is air from air. The wavelength is incident from air to a medium, so air is having a refractive index of 1, and for medium we are going to find out. So we can use the Snell's law. You can say refractive index of second medium, let us suppose that is given as mu 2. So Snell's law, and this gives us mu 1 sine of incident angle will be equal to mu 2 times sine of refracted angle. Here mu 1 will be equal to 1 because of the air. Therefore we can write that our mu 2 will be the ratio of sine of incident angle and sine of refracted angle. Incident angle is our 45 and refracted angle is 30. We can, this is sine of 45 sine of 30, and we get this will be equal to Sine of 45 is 1 by root 2, and sine of 30 is your half. So this comes as 2 root 2. So we can just rationalize it. This gives us that our mu2 will be equal to square root of 2. So we found out the refractive index of the medium. Now we can use the relationship that refractive index of a medium is equal to c upon v. C is the velocity of the light, and speed of the light in a vacuum, and v is the velocity of the light in the medium. Now we can find out the wavelength of the second medium, that is our lambda 2. Wavelength in the second medium, which is our lambda 2, and we know that our mu2 will be equal to c upon v, where c is the velocity of light in the vacuum and v is the velocity of the light in the medium. And this can be further written as that mu2 will be equal to c upon lambda, and this is lambda 2, and we have frequency, that is our mu2. And let me write the general formula, then we can divide into two parts. So we can write that our mu will equal to c upon v. This comes as c upon our lambda multiplied by frequency. So therefore we can write that mu1 will be equal to c upon lambda 1 nu 1, and mu2 will be equal to c upon lambda 2 upon mu2. And the frequency does not change whenever the wavelength passes from one medium to another medium. Okay. You can say that frequency does not change. So we can say our nu 1 is equal to nu 2. And we can find out the ratio. So ratio comes as mu1 upon mu2 will be equal to c upon lambda 1 nu 1 multiplied by c, this becomes lambda 2 upon nu 2. C and nu 1 nu 2 goes away, and we are left with this will be equal to lambda 2 upon lambda 1, and we are supposed to find out the lambda 2. So therefore we can write that our lambda 2 will be equal to mu1 upon mu2 and multiply by lambda 1. Mu1 is our 1 and mu2 is square root of 2, so this becomes our lambda 1. So the relationship between the wavelength is lambda 1 divided by square root of 2. So the option frequency is going to remain same, and lambda 2 is square root of lambda 1. So option number 2 is the correct one. Option 2 is correct. Next question. It states that a pole is vertically submerged in a swimming pool such that it gives a length of shadow 2.15 meter within the water when sunlight is incident at angle of 30 degree with the surface of the water. if swimming pool is filled to a height of 1.5 meter, then the height of the pole above the water surface in centimeter is. The refractive index of water is given as 4/3. So based on the information, we can draw an approximate figure for that. And let us suppose this is our pole and this is our A and our B, and let us suppose this is our, you can say, point O, and up till where we have a water and its height is given as 1.5 meter, and the shadow is said to be of the length 2.15 meter. So let us, okay, before that we are given that the sun is making an angle of 30 degree, yeah, with the surface water. So this angle will be over 30 degree. So with respect to normal, this angle will be over 60 and it will be reflected in this direction, and we can just draw the length of the pole, which is something like this, and this is A, B, let us call this as C, and this C, and this is D. So we need to find out our AB. Okay. This is O, and let us call this as O prime. And let us assume that we can use Snell's law. This angle, let us call this as R. So Snell's law at O prime Snell's law at O prime, let us call this as mu1, this as mu2. So we can write our mu1 sine of I will be equal to mu2 sine of R. Mu1 is our 1 and mu2, the water, is given as 4/3, and sine I is our 60 degree. Therefore we can write that 1 multiplied by sine 60 is equal to 4/3, and we have this sine of R. And from here, sine 60, this will be equal to sine 63/2. Therefore we can say that our sine of R will be equal to 3√3 and divided by 8. And from here we can easily find out our tangent of R. So we can say our tangent of R will be equal to, according to trigonometric identity, that is sine of R, and here we have 1 minus sine of R and whole square and its square root. Basically it is sine oblique cos, and cos we can write in the form of the sine. So we get this as square root of 3/3, and this comes as square root of 37. From here we can find out our, this height we already know, this height is our 1.5. Therefore we can write that our tangent of R will be equal to this CD multiplied by O prime C. Therefore we can write that our CD will be equal to O prime C multiplied by tangent of R. O prime C is 1.5. This comes as 3√3 and square root of 37. And this is approximately equal to 1.2 0.28. So we found our CD, and now we are going to find our AC, and this total length is given to us. This total shadow is our 2.15. So we can say our AC will be equal to AD minus CD. AD minus CD, and we have our AD is our 2.15 minus, and this comes as 1.28, which is close to 0.86 meters, and we need to find out our, you can say, we need to find out our AB, and AB will be equal to this AO plus OB. So you can say our AB will be equal to AO plus OB, and our AO is given to us, that is 1.5, and OB can be written in because AC is same as OO prime. So this AC is same as our OO prime. Therefore we can write from here that our AC is equal to OO prime, which is equal to 0.86 meters. So this comes as 1.5, and plus, okay, we only need to find out OB. We don't, there is no need to find AB, my mistake. We need to find out only our OB. So OB will be equal to our OO prime and tangent of 30 degree, and this comes as OO prime is 0.86 multiplied by tan of 30. So this gives us that OB is approximately equal to 0.51, and this can be approximated as 50 centimeters. Yeah, we know above the surface. This is our 50 centimeter. Next question. It states that a 2 meter long scale with a least count of 0.2 centimeter is used to measure the location of object on an optical bench. While measuring the focal length of the convex lens, the object pin and the convex lens are placed on at 80 centimeter mark and 1 meter mark respectively. The image of the object pin on the other side of the lens coincide with the image pin that is kept at 180 centimeter mark. The percentage error in the estimation of the focal length is. So we need to find out the estimation in the error of the focal length. And for that, first of all, we are going to use lens formula to find out the value of focal length, and then we are going to find out the percentage error. And we already know the formula that for lens we have 1 upon f is equal to 1 upon v minus 1 upon u. Let us call this equation number 1. And we are given that our u is our 100 plus minus 0.2 minus, and this comes 80 plus minus 0.2, and this comes as 20 plus minus 0.4 centimeters. Now we can find out our v, V will be equal to 180 plus minus 0.2 minus 100 plus minus 0.2. This gives us 80 plus minus 0.4 centimeters. So we were able to find out the position of the image and position of the object with respect to pole. Okay. And if we substitute the values, we get that our using equation 1, we can say 1 upon f is equal to our V is 80 minus of, and this comes as U is of minus 20, so this comes as minus of 20, giving us 180 plus 20, and sorry, this is 20, and LCM is 80, and this comes as 5 upon 80. So therefore, and this goes by 16, so I can say the focal length is equal to 16 centimeter. Now in order to find out the percentage error, we differentiate equation 1. In differentiating equation 1, we can write that our df upon f square is equal to dv upon v square plus du upon u square, and we are given the respective values as well as their errors. So we can write this as df upon f square is equal to, with respect to image, that is our v, it is 0.4 divided by 80 square plus, and this is 0.4 divided by 20 square, which comes as 0.4 we can take as common, so this comes as 1 upon 6400 plus 1 upon 400, and we can take 6400 as common LCM, and this gives us 0.4 multiplied by, this comes as 16 plus 1 17. So from here we can write that percentage error in the df focal length will be equal to, this comes as 0.4 multiplied by 17 divided by 6400 and multiplied by the focal length square, that is of 16 whole square, and this comes as approximately equal to 0.272. Now we can easily find out the percentage error. Percentage error, we can write this as, df upon f multiplied by 100, and we can say this will be 0.272 divided by 16 and multiplied by 100, and this comes as will be approximately equal to 1.70%. So option number 3 is the correct one. Option 3 is correct. Next question. We are given two vertical parallel mirrors A and B are separated by 10 centimeter. A point object O is placed at a distance of 2 centimeter from the mirror A. The distance of the second nearest image behind the mirror A from mirror A is. So here everything is given with respect to mirror A. Okay, let me draw this figure again. So this is our mirror A and we have mirror B, and the distance of the object is given with respect to mirror A, that is about 2 centimeter. So this is our object and its distance is given from the mirror A is 2 centimeter. And finally we have to calculate the nearest image behind mirror A, and that is also from mirror A. So everything is given with respect to mirror A and we have to calculate it with respect to mirror A. So therefore with respect to mirror A, we can say there will be an image that will be 2 centimeter somewhere here. This will be 2, and let us call this as mirror image I1. Okay. And this distance, the distance between the two is given to us as 10 centimeter. So we have this distance will be 8, and because of this mirror B, there will be image formed somewhere here. Let us call that as I2, and it will be also at a distance of 8 with respect to I2. So therefore, now we have to find out the position of the second nearest image behind A. Okay. So we can just write all these things. So we say that first position of the first image behind mirror A. Position of first image behind A. Okay. And in this case, we have said that is our I1. We have this I1, okay. And you can say distance, let us call this as X. So we can say that distance of I1 behind mirror A, which we call that X, will be equal to 2. And this distance, let us call this as D, which is given to us as 10. Therefore, we can say that can say the position of first image behind mirror B. Position of first image behind mirror B, here we called it as I2. So the distance of object from mirror B is our, because this is X, so this will be also our X. Okay, so this distance will be D minus X. So we can say the distance of object from mirror B is equal to over D minus X, which is 10 minus 2, giving us 8 centimeters. Therefore, the first image behind mirror B is 8 centimeter. That is of I2. So you can say first image behind mirror B is at 8 centimeter. Now this image, that is I2, will act as an object for mirror A, that is for second image. So now we are going to find out the position of the second image. The position of the second image behind mirror A, which is our final position of the image that we are required to find according to the question. So position of the second image behind mirror A, let us call that as our I2. Let us call this I3. I3, and this I2 will act as an object for this mirror I3. So we can say that image I2 acts as an object for mirror A. So we can find out the object distance from mirror A. So you can say distance of I2 from mirror A. Distance of I2 from mirror A, and that will be equal to our D plus D minus X. D plus D minus X, and which D is our 10, and is 10 minus 2 will be coming as 18 centimeters. So from here also we can clearly see that this entire distance will be over 18 centimeters. This is 8 plus 8 and plus 8 plus 2, sorry. And now because of the, you can say, the second image will be at a distance of 18 with respect to this A. Okay, so we can draw our I3 will be somewhere here and at a distance of 18 centimeter from mirror A. So we can say that the second image which is our I3 is at 18 centimeter behind mirror A, which is our final requirement. Okay, we come to the next question. And it states that two transparent media having refractive indexes 1.0 and 1.5 are separated by a spherical refracting surface of radius of curvature 30 centimeter. The center of curvature of the surface is towards the denser medium, and a point object is placed on the principal axis in the rarer medium at a distance 15 centimeter from pole of the surface. The distance of the image from the pole of the surface is. So we given a spherical refracting surface and the curvature is towards the denser medium. Okay, so we can draw an approximate figure for that. So let us suppose this is our denser medium and given as mu2 1.5, and this is our mu1 that is given as 1, which is our rarer medium, and the object is kept in the rarer medium. Let us suppose this is our object O, and this is our pole. This distance is given as 15 centimeters. So this is our denser medium, and this we have as a rarer medium. And we have to find out the image of this object where it will be formed. And in this case, we are going to use the formula for, you can say, refraction because of the spherical surface. So we can say that refraction due to spherical surface, and the formula is our mu2 upon v minus mu1 upon u is equal to mu2 minus mu1 upon r. Here mu1 is the rarer, or basically you can say the incident medium, and mu2 is our refracted medium, that is a denser medium. And the values are given to us. Here u will be our minus of 15, and radius of curvature is given to us 30. Mu2 is 1.5 and mu1 is our 1. So we can just substitute the values, and that way is going to give us directly the answer. So mu2 is a 1.5, v minus mu1 is over 1, and this is minus of 15 is equal to 1.5 minus 1 and divided by 30. This comes as 1.5 divided by v, and 1 upon 15. This gives us 0.5 divided by 30, and 0.5 divided by 30, it will be nothing but 1 upon 60. So we get that our 1.5 divided by v is equal to 1 by 60 minus 1 by 15. LCM will be equal to 60, and this comes as 60, this comes 1 minus, and this we have 4. This comes as minus of 3 upon 60 will be minus of 1 upon 20. Now we can easily find out our v, that our v will be equal to, this comes as minus 1.5 into 20, and we get that our v will be equal to minus of 30 centimeters. And yeah, so this was the next question. It states that an object is placed at a distance of 12 cm in front of a plane mirror. The virtual and erect image is formed by the mirror. Now the mirror is moved by 4 cm towards the stationary object. The distance by which the position of the image would be shifted will be. So we are given that we have a plane mirror, okay, and the object is placed 12 cm from the in front of the plane mirror. So let us draw its approximate figure. So this is our plane mirror, and let us suppose this is the principal axis or the center point. Here we have an object, and the distance of the object is given as 12 cm. Okay. And corresponding to this object there will be a image and which will be at the same distance. So let us suppose this image I, and its distance will be about 12 centimeter, and this image is with respect to object O. Now it is said that the mirror is moved by 4 centimeters toward the stationary object. Okay. So let us draw a relative figure for that. This was the original position of the image mirror, and we have an object, position is fixed, and corresponding this image is of I. Now the the mirror is shifted by a distance of 4 centimeter. So this distance is about 4 centimeter. So therefore the distance between the object and the mirror will be about 8 centimeter now. And the image that will be formed with respect to new position of the image, new position of the mirror will be also over the 8 centimeter from the mirror. Okay. So let us say the new image is our I prime, and this distance is our 8 centimeter. But from new position of the mirror, the original image will be now, this distance will be equal to now 16 centimeter. Okay. This will be 16 centimeter. And we need to find out only one thing, that the position of the new image. Okay. So the position of the new image will be shifted by 8 centimeter. Okay. This is the basic question here. So let me write it. We know that for plane mirror, distance of the object is equal to distance of object is equal to the distance of the image. We can say object distance, shorter form. We can say object distance will be equal to image distance. Let us call this as case 1 and this as case 2. Therefore, for case 1, the object distance, let us call this point as P and this point as P prime. So we can say for case 1, object distance is equal to our OP, which is our 12 centimeter. Therefore, we can write that the image distance will be our PI, and that is equal to 12 centimeter. Now we come to the second case. For case 2, object distance is now OP prime, and that comes as 8 centimeter. Therefore, the image distance that is our P prime I prime will be also equal to 8 centimeter. Okay, that is our final required answer. Next question. It states that a point object O is placed in front of two thin symmetrical coaxial convex lenses L1 and L2 with focal length 24 cm and 9 cm respectively. The distance between two lenses is 10 cm and the object is placed 6 cm away from L1 as shown in the figure. The distance between the object and the image formed by the system of two lenses is. So the basic figure is given to us, two lenses L1 and L2, and the object is placed at a distance of 6 meter. Sorry, it has to be centimeters, not meters. Let me write it. It places at 6 centimeter. So this is a centimeter and this is also centimeter. It's not meters. And the focal length of L1, let us suppose that is a F1, that is given as 24 centimeters. For F2, that is for L2, is over 9 centimeters. So object is in front of L1. So first of all, let's find out what will be the position of the image that will be formed by L1 lens, and that the image will be acting as object for our L2, and that will be giving us a final, you can say, image. So we start for lens L1, and we can write 1 upon V1 and minus 1 upon U is equal to 1 upon F. Here U is our minus of 6 centimeter. Let me call this as U1 and let us call this as F1. So we get 1 upon V1 plus 1 upon 6 is equal to F1 is 1 upon 24. This gives us 1 upon V1 is equal to 1 upon 24 minus 1 upon 6, and 24 is the LCM. This comes as 1 minus 3, 1 minus 4, so this comes as minus 3. Therefore, we get that our V1 will be equal to minus of 8 centimeters. So the image will be minus of 8 centimeter. So it will be somewhere here. Let us call this as about 8 centimeter. Let us call this as I1. And now we are going to find out for our L2. And this V1 will be acting as object for L2. So you can say for L2, image I1 acts as an object. So from here we can find out our, you can say, U2. So U2 will be the total distance, and this total distance will be 10 plus 8, that is about 18 centimeters. So U2 will be equal to minus of 18 centimeters. And we need to find focal length is given to us, that is our F2 is about 9, and we need to find out our U2, V2. So same formula, we can write that 1 upon V2 minus 1 upon U2 is equal to 1 upon F2. So 1 upon V2 plus 1 upon 18 is equal to 1 upon 9. So this gives us 1 upon V2, 1 upon 9 minus 1 upon 18. And 18 will be the LCM. So we get 1 upon V2 will be equal to 18, and this comes as 2 minus 1, that is our 1, which gives us that a V2 is equal to 18 centimeters, and this is with respect to L2. Okay. So therefore we are going to get that the image, final image, that is our V2. Let us call that image as our I2, and that image will be somewhere here. This is I2 at a distance of 18 centimeter from our L2. Okay. So the final answer is our 18 centimeter. Oh sorry, we need to find out a distance between the object and the image. So the object is our 8 and this is our 18 and plus 10. So total distance, we need to find out the total distance. So this is from 18 plus 18, which comes as, one second, sorry, it's not, we need to find out for the object. Object is here and this is our I2. So this distance will be equal to 18 plus 10 and plus 6. This comes as 34. So you can say distance between the object and final image. Final image is of I2 and this will be equal to 18 plus 10 plus 6 will be equal to 34 centimeters. This is the final answer. Next question. It states that the critical angle of a denser rarer interface is 45 degree. The speed of light in the rarer medium is 3 into 10 to the power 8 meter per second. The speed of light in the denser medium is. So we are given the critical angle of a denser rarer medium. So it means for critical angle, the angle of refraction is equal to 90 degree. So we can draw an approximate figure. So let us suppose its refractive index is given as mu2, rarer medium mu1, and we have critical angle. Therefore it will be just grazing the surface. Angle of refraction will be equal to 90 degree, and this is a critical angle C. So we know the relationship between the critical angle and the refractive index. So you can say for critical angle C, we can write that our sine of C is equal to 1 upon mu2, and critical angle is given as 45. So we can write this as our mu2 will be equal to 1 upon sine of 45, and this gives us that mu2 is equal to square root of 2. So we found out the refractive index of the medium, and this is our denser medium and this is our rarer. And we know the relationship between for a medium, we can write that refractive index for a medium that is our mu2 is equal to c upon v. C is the velocity of light and v is the velocity of the light in that particular medium which we are supposed to find out. C we already know is 3 into 10 to the power 8 and divided by v. So this gives us that our v will be equal to 3 into 10 to the power 8 divided by mu 2. Mu 2 is square root of 2. So we get our v will be close to 2.12 into 10 to the power 8 meter per second. So option number 2 is the correct one. Two is correct. Next question, and it states that the radius of curvature of each surface of a convex lens having a refractive index 1.8 is 20 centimeter. The lens is now immersed in liquid of refractive index 1.5. The ratio of power of the lens in air to its power in the liquid will be x is to 1. The value of x is. So we are given a lens and that is initially in the air and then it is put inside the liquid. And we have to find out the ratio of the power is given to us, that is x is to 1. So we have to find out the power of the lens and take out the ratio when it is in air and when it is in the liquid. So we are given a refractive index of lens is given to us. Let us call this NL, which is over 1.8, and refractive index of the liquid is also given of liquid, and let us call that as let us call this as N1 and this is N2, and that is given as 1.5. And we are also given the radius of curvature of each surface. Okay, so one will be positive, another one will be negative. So we are given the radius of curvature R1 plus 20 and R2 will be minus of 20. We can use the standard formula, that is our lens maker formula, that is 1 upon n minus 1. So you can say lens maker formula, we can write our f upon L will be equal to this, we have N1, let us call this F1, 1 R1 and this is our R2, and this F1 is focal length of air. Okay, lens maker formula for air as medium. And in this case it will be over n, and then later on we can put that n will be equal to n1. So we can write this will be equal to our n1 minus 1, and here we have our R1 minus R2. We substitute the values, we get this as 1.8 minus 1, and this comes as 1 upon 20 plus 1.20. So we get from here that 1 upon F1 is equal to, this will be our 1.6 upon 20. So the power P1, which is equal to 1 upon F1, will be equal to 1.6 divided by 20, and this can be written as 8 upon 100 or 0.08 diopter. Now we can come to the liquid. We can say medium as a liquid. For liquid, we can write 1 upon F2 will be equal to n minus 1, and we have 1 upon R1 minus 1 upon R2. Here n is nothing but a relative refractive index. In the previous case it was in air, so it has to be divided by 1. Okay. Now in this case it is in a liquid which is having a refractive index, so we can write this as 1.8 divided by 1.5 minus 1, and this comes as multiply by 1.20 plus 1 upon 20. Therefore we can get 1 upon F2 will be equal to, this will be our 1.5 and 1.8. 1.5, 1.8, yeah. So we can write this as 1.8 minus 1.5 and divided by 1.5, and this will be about 2 upon 20. And this will be equal to 0.3 divided by 1.5 multiply by 2 by 20, and this comes as 3 by 15. 3 by 15 goes by 5, so this comes as 2 by 100, or we can say 1 by 50. So therefore we can say that our P2 will be equal to 1 upon 50, and that will be coming as 0.02, and the ratio is given to us as x by 1. So we can say that the ratio air to the liquid, which is given as x by 1, will be equal to 0.08 and 0.02, and this comes as 8 by 2, and which is equal to 4 by 1. So therefore x is equal to 4. So value of x is our 4. Next question. It is given that one light ray is reflected from a plane mirror with a 30-degree angle of reflection. The angle of deviation of the ray after reflection is. So we have given that we have one light ray reflected from a plane of mirror, and angle of deviation we need to find out. So we are given a plane mirror. So let's draw a plane mirror. So suppose this is a plane mirror, and we have a incident ray. This will be a reflected ray, and angle is given as 30 degree. When one light ray is reflected from a plane mirror with 30-degree angle of reflection. Okay. So suppose this is our incident angle and this is our reflected angle, and if we extend this, we are going to get the deviation. This will be our delta, which we need to find out. So for the plane mirror, we know that our angle of incidence from plane mirror angle of incident is equal to angle of refraction, sorry, angle of angle of reflection. Okay, so we can write this will equal to about 30 degree. So this entire angle will be our twice of I. Okay, let us call this as A, this as our O, and this our B, and this angle is C. Okay. So we can say that our angle AOB will be equal to twice of I, which comes as twice into 30 is equal to 60 degree, and AC is a straight line, so angle will be 180. So we can write, we are required to find out angle BOC. So angle BOC will be equal to, that is our deviation will be equal to 180 minus twice of I, that is 180 minus 60, coming as 120 degree. So option number 2 is the correct one. Option 2 is correct. Next question. We are given, as shown in the figure, a plane mirror is fixed at a height of 50 cm from the bottom of a tank containing water, refractive index 4/3. The height of the water in the tank is 8 cm. A small bulb is placed at the bottom of water tank. The distance of the image of the bulb formed by the mirror from the bottom of the tank is, so we need to find out the image position of this bulb which is at the bottom. So in this case, so we have total tank is of 50, height of liquid water is 8, so this height will be our 48. And first of all, let us call the real depth of the, because it will be involving a concept of apparent depth. So let us write that the real depth of the bulb let us call this as D, will be equal to 8 cm. Okay. And refractive index is given to us 4/3. So we can say the apparent depth of bulb let us call that a D prime will be equal to D divided by refractive index. So we get this as D prime will be equal to our 8, refractive index is 4/3, which comes as 6 centimeters. So therefore we can draw with respect to the apparent depth this figure once again, and we are given a bulb. Let us suppose this is the depth of the bulb, which is about D, and the apparent depth which we found out is of D prime, so this will be about D prime. And we have a mirror that is somewhere here. And mirror is, let us suppose this is given as h height h. So total distance of the, you can say this was our object, and let us call this as apparent depth is of O prime. And so real depth is our D, which is our equivalent to O, and D prime is our apparent depth, which is our equivalent to O prime. So we can say distance of the object from the mirror. Distance of object from mirror, and that will be our H plus D prime. Okay, let me call this as point. For the sake of convenience, let us call this particular point as A. So this total distance will be our H plus D prime. So we can say this will be our AO prime, and that will be equal to H plus D prime. So we get our AO prime will be equal to, we have, sorry, it is 42, not 48. 42. So H is our 42. So this comes as 42 plus 6, coming as 48 meters. So in case of the mirror, the distance of the image and distance of the object is same, equal rather. So here we can say the image will be formed somewhere here. Let us call this as image I, and its distance will be equal to 48. Let's call this as I prime rather. Therefore we can say that for plane mirror, object distance is equal to image distance. So therefore we can write that our AO prime will be equal to our AI prime, and that is equal to 48 centimeters, not meters, centimeters. So we have this as a, from the bottom of the tank. Okay, so from the bottom of the tank, the total will be equal to this. We have 48, and from the bottom of the tank, this total distance is given to us as 50. So we need to find out from the bottom of the tank. So we can say that from bottom of the tank, that will be equal to 50 plus 48 is equal to 98 centimeters. Next question. We are given that an ice cube has a bubble inside. When viewed from one side, the apparent distance of the bubble is 12 centimeter. When viewed from the opposite side, the apparent distance of the bubble is observed as 4 centimeter. If the side of the ice cube is 12 centimeter, the refractive index of the ice cube will be. So here we are given that ice cube, let's draw its approximate figure. So this is suppose of ice cube, and the side is given as 24 centimeter. So this is given to us as 24 centimeter, and if observed from one side, apparent distance is 12 centimeter. So let us say when observed from the left side, this is the bubble, let us call this as O, and this distance is given to us as 12. And when observed from the other side, the distance is our 4 centimeter. Okay. Let me read it again. So let us put this is 12. This is O, and from the other side, let us put this is O prime, and the distance is about 4. And let us call this a distance D1, and this distance as about D2. This is point A and this is point about B. And thickness, let us suppose, is given as T. So we can say that for apparent distance from left side, distance from left side, let us call that a D1, which is our AO, and that is about 12 centimeter. And apparent distance from right side, let us call that as a D2, which is our BO prime, and that is about 4 centimeter, and thickness is given to us as 24 centimeter, that we called as T. Thickness of ice cube T, let us suppose that is about 24 centimeters. And we need to find out the refractive index, so which is basically real depth upon apparent depth. Okay. And for the sake of convenience, let us assume that the real depth of the bubble is at a distance x from the left side. From any one side, let's assume from the left side. So this is the real depth, and this is at a distance of x from our left side. So automatically from the other side, it will be equal to 24 minus x. You can say let the real depth, or we can say real depth from left side is equal to x centimeter. Therefore, real depth from right side will be equal to T minus x. And refractive index, the formula we already know, that our refractive index will be equal to our mu, and that will be equal to the apparent depth divided by the real depth. Apparent depth divided by real depth, and real depth upon apparent depth. Real depth is for first case. So we can say for the first case, this mu will be equal to x upon d1, and for the second case, this mu will be equal to t minus x upon d2, and we can equate these two terms. You can say x upon d1 is equal to t minus x upon d2, and if we substitute, x upon 12 is equal to 24 minus x upon 4. Now this we need to solve for x. So if this comes as 4x is equal to 24 into 12. So this will be coming as 288 and minus 12x. And 12 plus 4 is 16x is equal to 288, giving us that of x will be equal to 288 divided by 16. So x we found out is about 18 centimeters. And we need to find our refractive index. So you can say our mu will be equal to our 18 divided by d1. d1 was our 12. This comes as 3 by 2, that is 1.5. So the option number 2 is the correct one. Option 2 is correct. Next question, and it states that two convex lenses of focal length 20 cm each are placed coaxially with a separation of 60 cm between them. The image of a distant object found by the combination is at dash centimeter from the lens. So we are given that there are two lenses. So let us draw an approximate figure for that. And let us suppose this is lens L1, and they are coaxially we have a lens L2 as well. L1, L2, distance between the two is given as 60, and we are given that the image of a distant object found by the combination. So let us assume that we have an object which is somewhere here. So this is our object O. So let us solve it for L1 refraction, because the object is closer to L1. So we can say for L1 we can use the lens maker formula, and it is said that the object is distant, so therefore this u will be equal to infinity. And the focal length of f1 is given to us 20. Both have same focal length. So therefore we can use the formula 1 upon v minus 1 upon u is equal to 1 upon f. So let us name them 1. And we get this as 1 upon v1 minus 1 upon infinity is equal to 1 upon focal length is our 20. So this gives us that our v1 is equal to 20. Let us call this as I1. So this I1 will be, let us suppose, somewhere here. So this is our I1 at a distance of 20. So this I1 will be acting as an object for our L2, and distance of the object from L2 will be 60 minus 20, that is 40. So you can say that for L2 I1 will act as an object. So therefore its distance, that is our u2, will be equal to 60 minus 20, which comes as 40. Okay, and this is your minus sign. Focal length, that is f2, is once again 20. So once again we are going to use the lens maker formula, and we can write that 1 upon v minus 1 upon u is equal to 1 upon f, and 1 upon v2, this comes as plus 1 upon 40 is equal to 1 upon 20, giving us 1 upon v2 is equal to 1 upon 20 minus 1 upon 40. and 40 will be our LCM, so this becomes 2 minus 1, so this will be 1 upon 40. So we get our V2 is equal to 40 centimeters. So the image, let us suppose it is somewhere here, that is our I2, this will be our 40, and we call that as I2, and we have to find out the distance from the first lens. Okay. So this total distance, we have 60 plus 40, which is equal to 100. So we have this as 100 centimeter. So distance from the first lens, distance of I2 from first lens from L1 will be equal to 60 plus 40 is equal to 100 centimeters. Next question. And it states that the vessel of depth D is half filled with oil of refractive index N1 and other half is filled by water refractive index N2. The apparent depth of the vessel when viewed from above will be. So we can just draw an approximate figure, and this we have half filled by, okay, so total depth is D, and we have half filled by, this will be D by 2, as well as this will be also D by 2, and oil refractive index is given as N1, so this will be N1 and this will be N2, and observer is somewhere here. Okay, so there will be, you can say, apparent depth, we have to find out. So apparent depth will be the combination of apparent depth because of the oil and because of the water. So we can say that our apparent depth that is about D prime will be equal to apparent depth of oil plus apparent depth of the water, and we can write that D prime will be equal to, this is about D2, D by 2 rather, and N1 plus D by 2 divided by N2, and D by 2 we can take as common, so this comes as LCM N1 N2, and this becomes N2 plus N1, and which we are required to find out, and we have option number 2 is the correct one. Option 2 is correct. Next question, and it states that a fish rising vertically upward with a uniform velocity of 8 meters per second observes that a bird is diving vertically downward towards the fish with a velocity of 12 meters per second. If the refractive index of water is 4/3, then the actual velocity of the diving bird to pick the fish will be. So here we have a fish as well as bird, and the fish is inside the water, so there will be, you can say, because of the water it will be related to your apparent depth. So we can just draw an approximate figure. We have a liquid, and inside there is a fish. So let us suppose this is a fish, and it is moving in upward direction with a velocity of 8 meters per second, and above there is a bird which is moving in the downward direction with the velocity its velocity not given, but relative velocity is given, so let us call this as v. And there, we assume that the bird is at a height of y from the top of the water, and its refractive index, let us suppose mu, is given as 4/3. And we assume that fish is at a depth of x from the top of the water. So we can say that fish is at the depth of x meters, and bird is at height of y meters. Therefore, with respect to the fish, we can say with respect to fish, y prime will be equal to refractive index multiplied by y plus x. Okay. And from here, if we substitute the value, mu is given as 4/3, so this comes as 4/3 y plus x. And if we differentiate it, we get dy prime upon dt is equal to 4/3 dy upon dt plus dx upon dt. And we are given that dy prime by dt is our because the fish observes that the bird is diving vertically downward toward the fish with the velocity of 8 meters per second, and this velocity is observed by the fish. Okay, and the fish is moving upward and the bird is coming downward. Therefore, we can say that our dy prime, our dt, will be our minus of 12. So this comes as minus of 12 is equal to, we have this as 4/3 and dy by dt plus, and dx by dt is our 8. So from here we can just sort it out, and we can write this as 4/3 dy by dt will be equal to minus of 12 minus of 8. It is moving upward direction, it has to be minus. This is a minus of 8. This comes plus, and it will be coming as minus of 4. Therefore, our dy by dt will be equal to, this is our minus of 4 multiplied by 3 divided by 4. 4 and 4 goes away. So we get our dy by dt is equal to minus of 3 meter per second. So this is the actual velocity of the diving bird to pick up the fish, is our 3 meter in the downward direction. That's why it's a negative. Next question. second, minus, yeah, this is correct. Next question, it states that a biconvex lens of focal length 10 cm is cut into two identical parts along a plane perpendicular to the principal axis. The power of each lens cut is dash diopter. So we have a lens and this is our principal axis and it is cut along the axis which is perpendicular to the principal axis. So this is going to give us two lenses. Basically we are going to get it as a plano-convex lens. And we can use that it as a lens maker formula for each individual part. Let us call this as L1 and this as our L2. So the formula is our lens maker's formula, which gives us 1 upon f is equal to n1 n minus 1 1 upon r1 minus 1 upon r2. Okay. And this we are going to use into two parts. So first we are going to do it for original one, that let us call this as case 1 and this as our case 2. So we can say for case 1 we can write that our 1 upon f is equal to n minus 1 and 1 upon, you can say our r1 will be equal to r and our r2 will be equal to minus of r, this comes a plus r, and focal length is given to us 10 centimeter. So from here we get 1 upon 10 is equal to n minus 1 and this is our 2 upon r. And similarly we can let it sort it out. We can just write it as n minus 1 divided by r will be equal to, this will be coming as 1 upon 20. This we can use later on. So for case 2 and for case 2 we have two lenses L1 and L2. So we can write 1 upon f1 is equal to n minus 1 and this comes as 1 upon infinity and minus of r. So this comes and n minus 1 divided by r and this comes as 1 upon 20. So we get that 1 upon f prime will be equal to 1 upon 20 and the focal length of second one will be also equal to 1 upon 20. So for, let us suppose this will be our for L2. So you can say similarly for our L1 we are going to have same, let us suppose this is f double prime is equal to 1 upon 20 and from here we can write that our P1 will be equal to 1 upon f prime, that is equal to 1 upon 20 and this comes as one second, there is some Power of each lens. Okay, we have to find out the power of each lens, not combined. So the power of each lens will be equal to 0.5. One second, there is some. Okay, so we are given this in centimeters. Yeah, that's the problem. And for power, we need it to be in meters. Okay, so let me. So power in diopters will be equal to 1 upon f, and this focal length should be in meters. So we get this as 1 upon 0.2, and now it will be coming as 5 diopters. This is our 5 diopters. Next question. It states that the refractive index of a transparent liquid field in a equilateral hollow prism is square root of 2. The angle of minimum deviation of that liquid will be. Here we are given a hollow prism filled by a transparent liquid. Okay, so we can draw an approximate figure, and this is filled by a liquid. And we need to find out the angle of minimum deviation. So we have this as incident ray, this will be refracted, and this will be our emergent ray, and this is equilateral, so we are going to have this 60 degree, and the angle of deviation will be this one, that is our delta. And for minimum deviation, we know the formula that our mu will be equal to sine of, let us call this as A, B and C. We have sine of A delta m divided by 2, and this is sine of A by 2. And we already given, we substituted, this mu is given to us square root of 2, and here we have sine of 60 plus delta m divided by 2, and this is a sine of 60 divided by 2. 60 divided by 2 is 30, and that will be giving us, this will be equal to 1 by root 2 is equal to sine of 60 plus delta m divided by 2, which comes as sine inverse of 45 degree is equal to 60 plus delta m divided by 2. Now to a simple calculation, we get this as 90 minus 60 is equal to delta m. 90 minus 60 is equal to delta m, so our minimum deviation angle will be equal to 30 degree. Minimum will be 30 degree. Okay, so previous questions were all from the 2023 mains, and this question is from 2023 advanced question, and it states that a plane polarized blue light ray is incident on the prism such that there is no reflection from the surface of the prism. The angle of deviation of the emergent ray, that is delta, is 60 degree. The angle of minimum deviation for the red light for the same prism is 30 degree. Figure 2. The refractive index of the prism material for the blue light is square root of 3. Which of the following statement is or are correct? So we are having the same prism, but two different lights. One is a blue and the other one is a red. Okay. And both are plane polarized. In the first case, blue case, we are given angle of deviation is 60 degree, whereas for red it is given as that the angle of minimum deviation is 30 degree. So this is given to us. And in case of blue, there is no reflection. Okay. So everything is transmitted through the prism, where in case of red we can see there is a reflected also from one of the, you can say, faces of the prism. So in case of blue light, it says that there is no reflection. So it means the light is going to strike at a angle. That particular angle is called as a Brewster angle. So you can say that when light strikes a surface, at Brewster angle, it becomes plane, it becomes polarized perpendicular to the plane of incident, perpendicular to plane of incidence. So therefore there is no reflection observed in blue light. Okay. So it means the light must be polarized within the plane of incidence. You can see from here that the blue light must be polarized within the plane of incidence. So it means option number A is correct one. Option A is correct. So we can just draw the figure for this particular case and discuss it further also. And we have the incident light. This will be our refracted light and emergent ray. Let us call this as angle as R1, this angle as R2, angle of incidence, and this angle is angle of emergence, and this is our deviation delta, that is given to us 60 degree. Okay. And for Brewster angle, we know that tangent of I is equal to the refractive index, that is our mu. So you can say at Brewster angle, tan of I is equal to mu, and that is equal to square root of 3. from here we can easily say that our I is equal to 60 degree. And for a, let us suppose this is our angle of the prism, that is our A, and deviation is delta, so we can write for deviation, that is our delta, it will be equal to I plus emergent minus A. Deviation is given to us 60, incidence is also 60 plus E minus A. So this 60 and 60 goes away. So this gives us that emergent angle is equal to our angle of the prism. And we can use our, let us call this as point as P, this point as Q. So Snell's law at P, Snell's law at P, this gives us that mu1 sine of I is equal to our mu2 sine of R1. Here mu2 is equal to mu and mu1 is 1. So we can write that our sine of I, and we need to find out of R1, that is our mu2 is equal to sine of R1. So I is our 60, mu2 is square root of 3, giving us sine of R1. So from here we get that our R1 is equal to 30 degree. And we also know that our R1 plus R2 is equal to A. So from here we can write our R2 is equal to A minus R1, and we can just write it as that our sine of so we can write this as sine of R2 is equal to sine of A minus R1. And we can use our Snell's law at our Q. Snell's law at Q, we get this as our mu2 sine of R2 is equal to mu1, and this will be sine of E, and R2 is equal to A minus R1. So it's not required actually, we can just formulate it directly. So we get this as mu2 is square root of 3, and here we have sine of R2 is our A minus R1 is equal to mu1 is our 1, and we have this sine of E, and R1 is our 30 degree. So we can write this as square root of 3 and sine of A minus 30 is equal to, and E is equal to A, so this becomes sine of A because our E is equal to A. And we open this trigonometric identity, we get this as square root of 3, and this will be equal to sine of A cos of 30 minus cos of A, and we have this as sine of 30 is equal to sine of A. And if we divide sine of A across, we get this as square root of 3. This, you can write this as sine of A cos of 30 divided by sine of A minus cos of A sine of 30 divided by sine of A is equal to 1. In the first term, this sine A cancels out, and we are left with square root of 3, and here we have cos of 30 minus, it becomes cot of A multiplied by sine of 30 is equal to 1. And we substitute the value of cos of 30 and sine of 30, and we already have square root of 3, so this comes as square root of 3 divided by 2, and cos of inside will be remaining as square root of 3 minus cot of A is equal to 1. Now we sort it out and write cot of root 3 cot of A is equal to 2 divided by root 3, and we get this as cot of A is equal to root 3 minus 2 root 3, and this becomes 3 minus 2, that is 1, that is 1 root 3. This gives us that our A will be equal to 60 degree, and for E will be also 60 degree because they are same. Okay. And this is for blue, everything for blue. Okay, so anything else that matches it? So angle of the prism is not 45, angle of prism is our 60, so option number B is incorrect. And next we have to find out the angle of refraction. The angle of refraction for blue light in air at the exit plane of the prism is 60 degree. Blue light in air at exit plane, yeah, it is 60 degrees, so option number D is correct. Because we just found out emergence angle, that is 60 degree. Okay, so option D is correct. Is correct. And now we have to find out for red, the only thing is left. So for red we are given it is an angle of minimum deviation, so we can directly use the formula. So for red we are given our delta M is equal to 30 degree. So we can use the formula that refractive index is equal to sine of A plus delta M divided by 2 and sine of A by 2. Prism is same in both cases, so for angle of prism is over 60. So we can write this as sine of 60 plus 30 divided by 2, and this is sine of 60 divided by 2, and this comes as 90 sine of 45, and this comes as sine of 30. Sine of 45 is 1 upon square root of 2, sine of 30 is 1 by 2. So we can write that our mu is equal to 1 by root 2, and this comes as 2 by 1, and we rationalize it, it comes as square root of 2, which is our refractive index, and this is for red. So therefore the option number C is the correct one. option C is correct. C is correct. Next question. It was also asked in the year 2023 advance, and it states that an optical arrangement consists of two concave mirrors M1 and M2 and a convex lens L with a common principal axis as shown in figure. The focal length of L is 10 cm. The radii of curvature of M1 and M2 are 20 cm and 24 cm respectively. The distance between L and M2 is 20 cm. A point object S is placed at a midpoint between L and M2 on the axis. When the distance between L and M1 is n by 7 cm, one of the images coincide with S, then the value of n is. So we are given the basic diagram. We have two, you can say, mirrors M1 and M2 and a lens L, and object is S is kept in between at the center between L and M2. So each side the distance will be 10 and this will be also 10. We have to find out the value of n when one of the images coincide with the S. It means the image should be coinciding with the object, which is our S. So we have to solve it by using multiple cases. So in the first case, we say that the ray of light is first going to pass through our lens L. So we call it as case 1, and this is refraction on lens. We can say our first refraction on lens L, and it is said that the focal length of L is given 10 cm. So indirectly this object is placed at the focal length of the lens L. Okay. So you can say that object is placed at focal point of L. Okay. So it means after refraction the ray will be moving parallel to the principal axis. So you can say that the rays after refraction is parallel to principal axis. Let us call this as P and this as A. So this is parallel to principal axis, that is PA. And therefore we can draw an approximate diagram for that also. So we have two mirrors. This is our principal axis PA, and we have a lens, and the distance is given as 20. This is our source, so this distance will be over also 20. So the light rays will be, after refraction, will be moving parallel somewhere like this, and it is going to strike here, and let us call this total distance as d, and this point will be the focal length of the mirror, and that is given to us as L1 is 10, radius of curvature is given. So radius of curvature is our M1 is 20, so its focal length will be 10. So we get this will be equal to our 10. So therefore this distance will be our t minus 10. So the rays after refraction is parallel to PA, and they are going to strike M1. So we can say that upon first refraction at M1, as incoming rays are parallel to the principal axis, as incoming rays parallel to principal axis, the image is formed at focal point, and let us call this focal point as capital F1, as focal point F1. So now the distance of the object, so this image is F1, and let us call this as, better to call it as I1. This is I1, and now this I1 will act as object to L after second refraction. For second refraction, we can say that for second refraction at the length L, I1 will act object for it. I1 will act as an object. Therefore, the distance of this I1 from L1, let us call that U. So U will be equal to minus d minus 10. Focal length is given to us, or rather we can say 20 divided by 10 centimeter. Now we can find out the image that will be formed by the lens L after second refraction. So we can say that 1 upon V minus 1 upon U is equal to 1 upon F, 1 upon V minus minus plus d minus 10 is equal to 1 upon 10. This gives us that 1 upon V is equal to 1 upon 10 minus 1 upon d minus 10. Let us call this equation number 1. Okay. Now this image, let us suppose the image is called as now I2. Now this I2 image will be acting as an object for M2. Okay. And it is said that the object and the image, because of M2, should be coinciding with S. Okay. So you can say that for M2, I2 will act as an object and image should be at 10 centimeter. So we already know we can say the image distance, and same formula we can write this as 1 upon v plus 1 upon u is equal to 1 upon f. Let us call this as v1 and let's call this as 2. This is our v2, u2 and f2. So we substitute the values and we get this as 1 second, d minus this, this will be acting on an object and the image should be at 10 centimeter. Okay, so we get this as minus 1 upon 10 and this comes as minus of d is our 20. D we need to find out. Yeah, so we can write this as 20 minus v and will be equal to minus 1 upon 12 because radius of curvature is given as 24. So we can write this as 1 upon 12 minus 1 upon 10 is equal to 1 upon 20 minus v, and this will be giving us v. 120 will be our LCM. This comes as 2, 1. 12 minus 10, so this will be over 2, and with minus will be equal to 1 upon 20 minus v. So we get that our v will be equal to 80 centimeters. Now we substitute this v in equation number 1. So you can say from equation 1 we get 1 upon 80 is equal to 1 upon 10 minus d minus 10, and from here we can find out our d. We get this 1 upon d minus 10 is equal to 1 upon 10 minus 1 upon 80. LCM will be over 800 and this comes as 80 minus 10, that is over 70, and this will be d minus 10, so this will be d is equal to 7 upon 80. Sorry. So we can write this as 7 upon 80, and we can write d minus 10 will be equal to 80 upon 7. So therefore d will be equal to 80 upon 7 minus plus 10 rather, and this comes as 70. 70 plus 80 will be equal to 150 upon 7, and this is equal to n by 7, and your value of n will be equal to 150. Now we come to the, you can say, next part, and in this part we can assume that the first reflection is at M2, and then we can divide into 3 subcases. Now the first reflection is at M2. So therefore, let me redraw the figure. So first refraction is M2. So this is our M1, M2, and we have a lens which distance is given as 20, and this is our source, and the first refraction is at M2. So it will be moving somewhere like this, and here, and similarly to the other side also. So this will be our approximate figure, and next we can just remodify it, and here we assume that the image is being formed at a focus f1, and in the second case we can assume that it is being formed at the center of curvature. So for that we can just draw another figure. So once again we have a source S. This will be and curvature, so it will be going like this and coming like this, similarly to the other side also. And this is a curvature, this is our M1 and this is our M2, and finally we can also say that the image is being formed at the pole of M1. Okay, for that also we can draw a separate figure. So this is, we have source S. So image is at curvature, sorry, pole of this, and similarly to the other side also in this way. And now we can just solve it. So we can solve it by using previous value which we just calculated. And 1 second please. Yeah, almost there. Okay, so these are the 3 cases which is possible when the first reflection is taking place at our M2. So therefore, we can say that for M2, we can write that 1 upon V1, and this will be plus minus of 10, and this is minus of 12. So here we can just easily find out that our V1 is equal to 60 centimeter. Okay. Then the refraction at L and we get that our U2 will be our 80 centimeter, and therefore we can write that our 1 upon V2 minus, and sorry, not 80 but 60. One second. So image will be, this is our case 1, and in this case the image is being formed at 60. So the image will be somewhere here. Okay, so let us call this as our I1, and this distance will be our 60, and for our lens the distance U will be equal to 80, and this is for, so this comes as 80, and rather it will be minus of 80 ray of light, this and in this direction, and this have a total distance of, that is 60 plus 20 is equal to 80. So it will be minus of 80, and we get this as minus of 80 is equal to 1 upon 10, and we get 1 upon V2 is equal to, this will be our 1 upon 10 minus 1 upon 80, and giving us 1 upon V2 is equal to, this we called as our I1, and we get this as 880 minus, so this will be our 70, so we get our V2 is equal to 80 upon 7. Now these two things will be same for the entire case 1, case 2 as well as case 3. The position of the image, that is, well, I1 will be at 60 because that is because of M2, and the refraction because of the M, that is forming as V2, and that is our I2. So these two things will be same for the entire. So let us consider case 1, and in case 1 the image is at this F1. So we can say that V2 is at the center. So case 1 is our, we can say, reflection on M2. Reflection on M2. So from here we can write our case 1, and we know that V2 is at the center. V2 is at the center. Therefore, we can say that our D minus 80 by 7 will be equal to 20, and this gives us that our D will be equal to 20 plus 80 by 7, and it comes as D is equal to, this will be 220 divided by 7, which is over n upon 7, giving us that our n is equal to 220. And next is our V2 is at the pole of M2. Case 2 is our V2 is at the pole of M2. Therefore, we can write that D minus 80 by 7 will be equal to 0, giving us D is equal to 80 by 7, which is equal to n upon 7. So we get this as that our n is equal to our 80. So, and radius of curvature, radius of curvature, and this f1 we already sorted out here, that is about 150. Okay. So we get that value of n can be 220, it can be 80, and it can be also our 150. So value of n will be possible of any these combination. Next question. It was also asked in the 2023 advance, and it states that in an experiment for determination of focal length of thin convex lens, the distance of the object from the lens is 10 plus minus 0.1 centimeter, and distance of real image from the lens is 20 plus minus 2 centimeter. The error in the determination of the focal length of the lens is n%. The value of n is. So we are given that the object distance in terms of error as well as image distance, that is real, in terms of error is given to us. So we can write our u is given to us as 10 plus minus 0.1, and v is given to us 20 plus minus 2. We can use the lens formula and find out our focal length, that is our f. So we can say our f, 1 upon f is equal to 1 upon v minus 1 upon u, and this gives us that our f will be equal to 1 upon v minus 1 upon u. We substitute the value, this is our 20 and this is a minus of minus 10. We get our f will be equal to, this will be coming as 0.05 plus 0.1, which will be equal to 1 upon 0.15, or you can write our f will be equal to 20 divided by 3. Now we are going to find out the error, so we are going to differentiate. Let us put this equation number 1. So differentiating equation 1, we get minus 1 upon v square dv plus 1 upon u square du is equal to minus 1 upon f square df. And for maximum error, we can write it as 1 upon f square df is equal to 1 upon v square dv plus 1 upon u square du. And we need to find out the percentage error, and we also know the values, so we substitute it. We get this as df upon f into 100 is equal to 1 upon v square dv plus 1 upon u square du multiply by f and multiply by 100. We substitute it, we get df upon f, that is percentage, will be equal to 0.2. V square is our 20 square, that is our 400 plus 0.1, this is our 100, multiply by focal length we just found out is our 20 divided by 3 and multiply by 100, and this will be equal to 1%, given in the question as n%, so value of n is equal to 1. Next question. So it was also asked in the year 2023 advance, and it states that a monochromatic light wave is incident normally on the glass slab of thickness d as shown in the figure. The refractive index of slab increases linearly from n1 to n2 over a height h. Which of the following statements is or are true about the light wave emerging out of the slab? So in this case, we are given a slab, so we can just draw a simplified diagram for it. So let us suppose this is our slab and its thickness is given as d and height is given as h. In this case we are given, let us suppose this is our A wavefront A and this is our B, and this is the position at t is equal to 0. Okay. So wavefront, we can just draw it like this. So at t is equal to 0, so this is the position, and the height between this is given as h, and we have the refractive index on the, here it is n1, and on the top it is given as n2, and it is given that n2 is greater than n1. So the emergence wavefront, we can approximate it, it will be coming something like this, making an angle of theta, and here we have to remember that n2 is greater than n1. And let us call this as A prime, B prime and C, and this distance we call it as x. So we can say that our A prime will be equal to velocity in the medium is c, then this is c will be equal to refractive index n2, and we can say our B prime will be equal to velocity in the medium divided by n1. Sorry, not velocity in the medium, but velocity in the c is the velocity of the light. And this position was at, okay, and B prime C, we assumed that it will be our x, and it is said that, okay, so we should be having that our time that the wave takes from A prime to A should be equal to time taken by the ray from B to C. It should be same. So we say time from A to A prime should be equal to time from B to C. and let us call this as time A to A prime is equal to time from B to C, and from B to C we can divide into two parts. We can say that time from B to B prime plus time B prime to C, and from time from A prime to time A to A prime, we can write this as distance is D, and this is our C multiplied by N2 is equal to TB prime will be equal to distance is same, and this is C multiplied by N1 plus, and refractive index is 1 for B prime C, and it will be equal to distance traveled is X divided by C. So here C cancels out throughout, and we can write from here that our N2 minus N1 times D will be equal to X. So the angle of deflection, okay, we need to find out angle of deflection. We can find out that also. Okay. So we can say tangent of theta will be equal to, we have this as X and H is the height, so this will be X upon H, and X we just found out is our N2 minus N1 multiplied by D and divided by H. Okay. So we can say that the deflection angle is dependent upon N2 minus N1, so this is correct option, and it is also given that our theta is our tangent inverse, so this is also correct option. Okay. So from here we can just find out our theta also. So theta is equal to our tangent inverse of N2 minus N1 times D divided by H. So option number B and D are correct. Option B and D are correct. Yes, so I think this completes this one also. So I think this was the last one. Yeah. So these were the questions from the year 2023 mains as well as advanced. So this completes all the questions, and in this we have used the approximation. Okay, if you want to draw the exact one, the result will be coming same. We can just draw the exact one also, because the wave front will be coming something like this. Okay. And they will be bending in this way, and this angle will be our theta. Okay. But anyways, in both the cases, this distance, because the refractive index is N2 minus N1, this will be coming as D, and this is height H. Either way, both of cases the answer will be same, it is not going to change. Okay. So we can just use the approximation and get the same result. So this completes the questions. Thank you.